Folks, when you're trying to create something new, there comes a time when your designs have been designs, you've engineered everything, you've completed your tests, you've reviewed your previous data, you've made changes, you've created your parts, you've written your software, and you end up back on the pad with something new. That is where Isar Aerospace is this evening. As you can see on the pad, Spectrum Flight 2 is coming live from Norway. This mission is named Onward and Upward. It is the return to flight for Spectrum. I'm John Galloway with NSF. NSF is providing launch media services for Isar Aerospace this evening. And with me is Nicholas Pedrakis. Nicholas, how are you doing?
I'm very excited to be here and also very proud to be representing Isar on this very historic day. Yeah, it's really great to be standing on the pad for the second flight.
Outstanding. Well, not quite on the pad. We're a little bit away from the pad. The rocket's on the pad.
We're referring to the rocket, yeah.
A distance away. Nico, you're the chief engineer for Spectrum.
I am, yeah. I'm leading the technical development of our launch system, meaning the launch vehicle and the ground systems. That means defining the technical direction, roadmap, and architecture for all of our systems, spanning from GNC, avionics, propulsion, fluid system, ground system, and so on and so forth. Yeah.
Absolutely. So Nico here is the correct person to have on the stream if we want to talk about technical systems this evening, which is what we plan to do. We'll talk about where Isar came from. We'll talk about the machine that they're going to be building to build these rockets en masse. We'll talk about the rocket itself, how it's built, the fuel that it uses, and all of those sorts of things. So we have quite a bit of content for you as the clock continues to tick down at T-minus 56 minutes and just about a half there. So this evening's launch is scheduled for 21:06 local time, putting us just under an hour away. And we have about a 15-minute window. Now, it's a night launch this evening, but we do expect Spectrum to be a very bright rocket with that propane engine.
Indeed, yeah, with all 9 engines lighting up in the first stage, it's going to be a bright object. This is driven essentially, so the time, both being a night launch and the duration of the window,
the 15-minute window.
Exactly, driven by the target orbit. So it's a sun-synchronous orbit, SSO as we refer to it, essentially has a property that satellites, in this case our customers, pass over the same location at the same local time with every pass.
It's kind of the shadows are the same every time. It's great for imaging.
Yeah. Exactly. So imaging, Earth observation, weather, it has this advantage that you have the same lighting conditions every single time.
Yep.
Yeah.
And from the map here, you can see we're zooming into northern Europe. We'll talk a little bit more about that later. To Norway on the island of Andøya. This is a spaceport location up here. And the land that the launch pad is on is actually new terrain that was put here. We're inside the Arctic Circle right now. We're 300 kilometers inside the Arctic Circle, about 190 miles. And that piece of land was not there before we wanted to put a launch pad there, was it?
Exactly. So if you were to show the same image from 3-4 years ago, you would just see a coastline at this point. So essentially we had to build, all through the civil works, build this small peninsula together with our partners of Andøya Space, AS6, and that's where the launch pad now lies and where our vehicle is standing.
And those are the shots we keep seeing over on the other side of the screen here, folks. We've got cameras all over the pad. We've got tracking cameras. We've got some experimental onboard video that we'll also try to share with you. But all the coverage that we can share, we are glad that you are joining us live this evening. Now, we do want to talk about the previous flight because this is Flight 2 of Spectrum. Let's talk about Flight 1, about a year ago.
Yes, exactly. It was on the 30th of March, so roughly a year ago. And we had successful operations throughout the auto sequence, throughout the ground phases. We have successful release of the vehicle and liftoff.
Right.
And we were able to verify propulsion systems, avionics structures for the first roughly 30 seconds of flight until we had a loss of attitude control and the termination of the vehicle.
Absolutely. They say a picture's worth 1,000 words, but we've got some video, so that's probably like 1,000,000 words. Yeah. Let's roll a recap of what happened during Flight 1. If there's an award for the most beautiful launch pad, I think Andøya is right up there in the running.
Definitely, we have a good chance of winning that award.
Absolutely. But Flight 1 did end in an anomaly, but it also ended in lots of data that you and your team have used to improve Spectrum for Flight 2.
100%. As we said, also for Flight 1, it was a test flight, meaning that we have all this valuable data that we take and transfer into learnings for the next versions of the vehicle, specifically also Flight 2. So we were able to verify a lot of systems during this first 30 seconds of ascent.
Yep.
So we learned a lot of, from every second of engine data, from every second of structural data, every second of avionics data, you get all these learnings that you then transfer into engineering decisions that you then apply into your second vehicle or verify your requirements with that. Obviously, there were also some anomalies, some of them minor, some of them major, but it is exactly the reason why we performed this test flight. Our main purpose is to obviously find a balance between simulating, testing on the ground, and then finally getting the courage of saying, yes, now we can fly.
Yep.
And this is where we get the most valuable data. So also specifically to the anomaly that we had that led to the termination, attitude control, we saw that there was a mismatch between what we modeled and the actual reality, which fed into our control algorithm and then finally led to this discrepancy and the actual non-conformity. This is something that we wouldn't have learned if we didn't get to the pad on this day, if we didn't fly the vehicle on the first flight.
Absolutely, and that is the process. I think a lot of people who are new to rocket chasing, I can call it that, don't understand. They think that every flight is supposed to be completely perfect, but when you're designing a new vehicle from the ground up, this is how it goes. You can't just simulate forever. You need to get real-world truth. You need to get actual flight data, and that's how you do that. You get on the pad. And the good news is that Isar wants to share that with us this evening. Look at the drone shot.
Oh, it's really impressive.
We will have all sorts of fantastic views, so please stick around. Also, send this to your friends and family. Let them know that a European company here is got a rocket on the pad ready to launch this evening. Now, Nico, I just said a European company. There are lots of companies that seem to be creating rockets these days. There are lots of rockets that we see flying. Why do we need another launch provider?
Well, it is true that the global launch activity is indeed accelerating rapidly. However, if we look at the numbers, Europe's launch cadence still remains comparatively low. If we just look at 2025, Europe had in total 8 launches, one of them being ours.
Right.
Compared to roughly 200 in the US or roughly 200 in the US or 100 in China. And there is a huge need there for European launch vehicles in order to ensure the independent and reliable access to space. So space has become an integral part of our lives and of our economies. And we need to have independent access to space to not rely on externals. This has strategic risks if we are lacking this capability, and especially when we are talking about geopolitical changes or changes in the global space market and space sector, we need to have this control of the entire chain, meaning having this very important infrastructure of being able to provide payload into space. And Europe lacks that. That's why we're here.
Absolutely. Space is such a critical platform. A lot of people don't understand how entwined in our daily lives that it is, and it's only going to get more entwined. So it makes sense that Europe should develop its own launch capabilities, its own systems to be able to put things into orbit. Now, the clock is continuing to tick, and we've just gone under T-minus 50 minutes as we continue to look at all the different parts of the pads. You'll see the venting, you'll see the rocket coming to life. We want to share all these views with you, but everything's looking good so far, isn't it?
It is. So far, everything looks great.
All right. So, Europe needs launch capabilities. But are there actually European customers who want to hire a company to need payloads launched?
Definitely. European global customers, we have a huge demand at this point. And again, it boils down to the same fact that spaceflight is a core element of life and economy. Sometimes, I think, especially for people who are not directly involved in space, there is a misconception that it's only for research or for space exploration or driven by government. However, we've shown that in the last 20 years, there is a private market, both in launch service and satellite providers. Aspects of life, as we said, like navigation, everybody uses GPS on their phones.
Yep.
That's relying on space. We have other aspects like time synchronization for bank transfers or networks for communication, phone networks, climate
weather satellites.
Exactly. Weather satellite, natural disaster monitoring, crop monitoring. All these applications affect our everyday life. And they all start with the same bottleneck, which is a launch. And that's the reason why we have all these satellite providers reaching out to us with a demand to get into space. And we're trying to match this demand with our supply.
All these satellite providers, are we talking like 3 satellite providers? Are we talking, how many are we talking about?
No, it's a much larger number than that. So actually our next flights are already booked out, and we want to make sure that we scale up our capability both in terms of production and operations in launching, in order to never be in a position where we have to turn down, customers because of this huge demand.
Makes sense. I mean, you're not just making up numbers here. You have actual customers that are coming to Isar saying, hey, we have payloads that need to be put into orbit. So it sounds like you've got a little bit of backlog. You better start making some more rockets.
Definitely. And that's also clearly our target, to reach to a cadence of tens of launches per year in order to fulfill this demand.
Absolutely. And this is driven by actual customers that you're talking to, not pie-in-the-sky PowerPoint numbers that somebody's made up because they want to start a launch business. Now, the clock continues onwards here, folks, as we stand by for the launch. We are now 47.5 minutes away from launch. But let's talk a little bit about, there's demand. Europe needs to be able to launch rockets. How do you create an entity? How do you create a company that can actually provide that for Europe?
So actually, Isar started roughly 8 years ago, and initially it was a spin-off from a university group called VAR, which is part of the Technical University of Munich. Now that's 8 years ago, and a handful of students. Now we're looking at 400 plus professionals. Okay, so it's a big change.
Wow.
Over the entirety of these 8 years. And a core mentality of this group from the beginning, of the company from the beginning, was to get to hardware testing as soon as possible. Obviously have the first designs, simulate and validate as much as you can, but most of the learnings happen through actual testing.
Right. Not just simulations or presentations or here's the things we're going to make. You actually need to make things.
Exactly. And in search of, getting to those facilities, getting these resources to test, funny story is that one of the first test rigs, which we're still using, was back in the day a cowshed, which was then transformed into a component test rig. Yeah.
A cow, like in a farmer's field, like a barn, a cowshed?
Exactly, yeah. And you got to be resourceful, use all the resources that you get, and essentially this was transformed to a very professional actual test rig where we did initial development of engine components, valves, and so on and so forth, and it's still actually in action for subcomponent testing.
No kidding.
And throughout the history, obviously we had to expand, apart from all designing and testing, we needed to scale up our production, so put a lot of effort in actually doing that, building this machine that builds the machine, going also to our full-scale test rig, expanding to our launch site, and 8 years later, we're now looking at the second vehicle standing on the pad.
That's outstanding. Now, it sounds like a group of folks who are passionate about being able to build this capability came together. I mean, putting the first component tests in a farmer's field, a cowshed, to get things going, to start getting that data, that really is an interesting sort of backstory. It's not, here we're going to make a bunch of money doing launches. It's, we need to provide this access for Europe, and that's how you got started.
Exactly. Yeah, seeing an actual need in this lack of, very frequent access to space and trying to fill it with a product.
Makes sense. Now, there are a lot of people. You said 400 people. I think we've actually got some interviews. We got a chance to catch up with some of the many talented people that work here. So let's check in with some of what the employees have to say about Isar.
So, working together with people from all over the world under the same vision, it's something really exciting.
So what I like most about working at Isar is that you cover the whole process from design to testing to launching.
So what makes Isar Aerospace so unique to me compared to other places I have been before is the various topics we are dealing with every day.
I'm really looking forward for the future of Isar Aerospace. We got a world-class manufacturing team, smartest engineers, beautiful product, a really nice launch site. Yeah, what else do you want more?
The excitement here, it's crazy because you can see the evolution of a full rocket from zero until the end.
So looking at my team, I think what comes to mind is teamwork and focus, especially if we are like in crunch time when it goes towards launch or to a stage test. You really feel the energy in the room and that everybody is trying to help out where he can.
What I like most working at Isar is that we're a relatively young startup still, so there's still a lot of room to grow. And we get to make a lot of the calls ourselves here, even as the young team as we are. So there's a big impact we can have on the future operations of this company.
Another unique is honestly is the people. It's you really see in every day how much they care, how much everyone comes here every day full of energy and passion, and everyone wants to do a good job, and they do.
And then also working with all these smart and talented people who make this happening and are so driven by this mission to launch rockets and to produce them.
I love working in this area, especially because of the freedom that this job gives you in the amount of things you can learn.
What I love about working at Isar is helping people working together towards a common goal, launching rockets.
I think we have the most amazing final product. Not a lot of other companies produce a rocket from scratch to the end.
The thing I like most about working in Isar Aerospace is the fact that we are extremely ambitious and that we are able to learn something new every single day.
The unique character of Isar Aerospace is the combination of ambition and responsibilities.
I love my job because every day is different. Many things happening at the same time.
The part that I love about working here is that you get to be a part of every step of the process.
What I like most of working with Isar Aerospace is I'm allowed to travel a lot. So I meet people in Norway, Sweden, Germany, and learn a lot about the cultures, and I have the best office view in the world, and look at that.
Positivity, focus and teamwork plays a very vital role into the work that I do and my team does on a general note.
And we truly are a team. So whenever I need help, I know I can count on my team members to come and help and get the job done.
I think the moment when I was most proud of our accomplishment was when I saw the software that we made being used during the launch operations.
I can feel the pulse is really getting high now as we approach to the second launch, and it's going to be really exciting.
There's one key thing that has driven me out of my life, and that's being part of a winning team.
I think it's been an incredible push from the whole company to get back here so fast as we did in 9-10 months to get to this point, and I would say everybody is ready to send it.
That's always been something I've wanted to say, that I've worked on something that's gone into space.
I believe this company is able to basically make anything happen.
Like you said, over 400 people, and as I watched the video, I've worked with some of the people there that are featured in the video, and everybody across the board is helpful. They want to solve problems. They're there to help you out when you need something. So,
yeah. And it's really moving seeing that video, actually. Like seeing all this passion and dedication of all the people. That's what brought us to the pad for Flight 2.
Yep. It's not just a rocket. It's not just physical components or machines or anything like that. It's really the people behind the organization that drive it.
Exactly.
Outstanding. So there are people from all over the world that work at Isar. You could see the diversity there in the video. How many different countries are represented?
It's a very international group. I would say roughly 50 nations work at Isar.
Okay.
Yeah.
And across the locations that you have a few different facilities.
Yes, and they all represent the fact that we're completely vertically integrated, right? We're spanning the entirety of the design process, building process, testing process, and launching process, and that's why we have also these different locations. So our headquarters are in Munich. That's when we do the engineering design and also production. We have a production hall.
Yep.
There is a test site, the ex-cow shed that I mentioned earlier, which is roughly an hour away from Munich. And then when it comes to full-scale testing of our engine, both development, acceptance, and qualification, we have our test site in the northern of Sweden, in Kiruna. And, of course, our launch pad here in the northern part of Norway, where we're standing today with our vehicle. At the same time, though, I have to say that we are in this process of scaling. I mentioned earlier, tens of vehicles per year.
Right.
And we can only do that with a production facility that can sustain that and can actually enable that. And that's also the reason why we're already moving this year to a new headquarters, still in Munich, in the east part. And that's where we want to build Europe's first commercial serial production facility for state-of-the-art launch vehicles that enables this high cadence of tens of vehicles per year. And we can actually see footage right now of this facility and its current status.
Yep. That's a cool little time-lapse there of the facility being built.
It is.
So it sounds like you're going to need some help to fill this facility out.
Definitely. I mean, we're scaling up production, operations, and to do that, we always need, obviously, brilliant people, not only in the engineering part, but also technicians and operators. We need all these talents to scale up the company to the tens of vehicles per year.
Right. Now, you don't just get to go down to the store and buy a rocket factory and then install it and, let's do that 3 times and make some rockets. It takes a lot of work to actually build it, which is what we're seeing there.
Exactly. You have to go out and actually build your own factory. You can just buy it, and that's what we call the machine behind the machine. Our key focus is not just making this product work once today. We need to show that it happens reliably and at a high frequency, and that's the part of industrialization and iteration. And actually, we can see footage of our current hall.
It's like a fly-through.
It is. It's a drone footage. It's a great video. We are right now in the additive manufacturing area. You can see some of the components for the engines that are now being brought out of the printer.
Right.
Exactly. And then we're moving towards the avionics lab, where we have harness production for stage 1, stage 2 of our vehicles. You can see that being laid out by our technicians and engineers. And then we're continuing the tour. Oh, yeah.
In the bin, it looks like, in the box.
So, yeah, you get to see what a part that's being transferred now to storage and then to milling would experience. So you can see the automated robot there that just places it to the correct shelf.
So this is moving it around the factory. These are automated parts because you're trying to scale this up. You're not hand making one part. You want to make lots of parts.
Exactly. You need to automate as much as possible to get to this capability, obviously.
Wow. I do want to shake the hand of the drone pilot that flew this around. This is actually really cool.
Yeah, it's really impressive work there.
And this is the current production hall. This isn't the new large production hall. This is the small. It's not small. The smaller production hall.
It's smaller. Yeah, it's definitely not small. I remember actually the original one.
Yeah.
It's the current production hall. I remember entering this hall maybe 6 years ago. It was an empty hall, like 50 times 50 meters.
Yeah.
I couldn't imagine at that point, to be honest, that it would be so filled with both machines and technicians, engineers, and also vehicles, engine parts. And now we've reached a point where we do need to get to a larger facility, roughly 10 times the area actually, just to get to this high cadence of producing the vehicles at the rate that we need.
Absolutely. I will say the big new buildings and stuff like that, and then everything that you've got here, plus all the people, sounds expensive. Like, how does all this get paid for?
Well, our company is privately funded, so there are investment rounds through different stages of the company that either supported the development of the launch vehicle or, as of recently, the industrialization of the launch vehicle, meaning the scale-up of our production facilities.
Right.
So the backing is from a broad set of investors, and that gives us essentially this support to go out there and do what we do.
Okay. We've been talking about a lot here, right? So let's do a little bit of a recap. Is there a market for launches? Yes. It sounds like there are things that need to go into space so that we can continue our way of life, right? Do we have some people who want to provide those services? Yes. The students who created the university group, I guess is the right way to say it, with the first test stands in the cowshed, right? So we've got a group of people. We've created a company, Isar Aerospace, and the factory that we just saw the fly-through of. Let's talk about the rocket itself. And the first thing I want to ask, Spectrum, why'd you name it Spectrum?
It's a cool name, first of all, but then it also stands
Looks good on a
for
shirt.
more than that. Yeah, it stands for more than that. So, first of all, the vertical integration part, we're covering the full spectrum of these operations, as we said, from initial design, from scratch, to building, testing, launching, and closing that loop. And at the same time, in terms of the capabilities of the vehicles itself, so it's a multifunctional vehicle configured to offer a broad spectrum of services. So these two combine, it was a natural progression of ending up with Spectrum.
It's almost like Spectrum Squared. There's like 2 spectrums involved here.
Yeah, exactly.
Excellent. So we'll talk about these systems in depth, but give us a rundown, like how big is the rocket, how much payload can it carry, and then we'll talk about some specifics like the structures behind it, the engines you've created, the fuel that it uses. Give us a rundown.
Yeah, very top level. I mean, Spectrum is a small to medium lift vehicle, meaning that it can bring up to 1,000 kilogram to low Earth orbit. It's a 2-stage vehicle, propelled by liquid oxygen and liquid propane in both of the stages, and actually uses 9 engines in the lower stage. First stage, and then 1 engine vacuum optimized for the upper stage. In terms of dimensions, just to give you an idea, it's roughly 28 meters high, 2 meters in diameter, and weighs roughly 55 tons.
Gotcha.
When fully fueled.
And you do all of this in-house, like you want to not just build 1 rocket or 1 rocket a year, you want to do this at scale.
Exactly. That's also a business model behind the company, building that at scale, reliably, frequently launching.
We've switched to the CNC channel here real quick. So,
yeah.
but again, all these machines in-house, parts being made, gives you some actual advantages to the work that you do. But let's talk a little bit about the engines here. I don't need to guess. You just told me they're developed in-house.
They are developed in-house. So designed, developed, tested completely in-house. Yeah.
For the propulsion fans out there, what sort of cycle is it?
So it's a gas generator cycle, meaning an open cycle. That was, in the beginning, when starting to develop the engine, it was very important to go out and test as many components as possible independently from each other, verify that they are set up to do the actual work they should be doing, and then putting everything together into an integrated system. So the gas generator cycle allowed us to do that using smaller scale testing without much of a coupling between the systems, and then putting everything together at the end. And also what was very important and ties together with the automation and industrialization part is having a single engine concept for both stages. So in terms of components, they're identical to 90%. Obviously some differences because they're also operating at different environmental conditions, but it was very important to us to reduce the number of parts that only have to be produced once for the upper stage engine.
Right.
If you can produce something 10 times instead of once, you can understand how much the cost can be driven down, how much time you save from having different designs, and so on and so forth.
So you hear about that sometimes, where the upper stage engine needs to operate where there's no atmosphere, right? In the vacuum of space as you sort of get going into orbit. But the first stage engines need to operate at sea level. They need to take off where the atmosphere, the air that we breathe is surrounding them. And so sometimes companies design 2 totally different engines for those 2 very different environments. But here, you've designed 1 engine that sort of fits both places, and you just tweaked it a little bit.
Exactly, yeah. Obviously, there are some tweaks that have to be done, but it was a requirement going into this design process to make sure that it's as similar as possible to the sea-level engine.
Gotcha. We flew through the 3D printing area earlier. Are parts of this 3D printed? You 3D print engines, I think, right?
Yes, we do several parts, both in the thrust chamber assembly, housings for valves, for example, for turbopump components, are 3D printing. We leverage this technology because it allows us to iterate very fast. So we've seen some crazy iteration times in development testing, going from testing on the test stand to a new design to printing, heat treating, milling, and then going back to Kiruna, to Sweden, to retest in a matter of a couple of weeks, which is extremely impressive. And it's enabled also to a part through the additive manufacturing component.
Gotcha. So we put together some engines. We need something to bolt the engines to, right? And that's where the composite structures come in.
Exactly. So structures, again, 90% of the weight of the Spectrum rocket is actual fuel, and this fuel is being held by the structures. What we keep saying internally is that structures have to be boring. Making them boring is not that easy, but essentially you don't want to start worrying about them. They need to obviously hold all the loads, and rockets experience a very harsh environment, both in terms of vibrations, in terms of static loads, accelerations, aeroacoustics, all these harsh environments, and that's the job of the structures to actually sustain that. And we have chosen linerless carbon tanks for
linerless carbon tanks.
So carbon fibers, reinforced polymer, but without a metallic liner on the inside.
Probably saves weight.
Exactly. That's the main advantage.
Okay.
Obviously, as I said before, we want to have a design that is reliable and easy to build, but at the same time, we can't compromise performance of the vehicle. And by going with these carbon structures, we're ending up with 4 times better strength-to-weight ratio than other metallic materials.
Right.
And at the scale or the size of our vehicle, it does make a difference.
Ah. I mean, I've heard people say, oh, composite structures, they're so slow, they're so expensive. A lot of people seem to sort of think they're not great, but we've advanced beyond that. We're not talking about people with big flaps of carbon fiber that they're hand painting on the thing. You've got some automation here so that you can do this at scale.
Exactly. This is necessary, as you said, to scale up. So automated winding and automated placement of these fibers is necessarily what we're doing for the majority of the primary structures. And yeah, this is how you get to a fast pace of producing vehicles.
Right. And you said something very important there. For the scale of your vehicle, right? Yeah. The composite structures make sense because you can automate them, because they're not overly sized, like insanely huge, the biggest thing ever, right? They fit in this niche, and you're making this work.
Yeah. If it was a different size, maybe we would have gone with a different technology, but for our particular size, it makes perfect sense.
Okay. So the fuel, I saw it there when we were at the pad. It said propane on the tanks real big. Like propane like my barbecue grill uses?
Similar, probably not exactly the same grade.
It's not space propane, I guess. But
yeah, space propane. We need to make sure that, you know, the impurities are reduced, obviously, but other than that, it's the same chemical element, or it's the same molecule.
Sure. Why would you choose that? I mean, I hear all these high-performance fuels or older fuels, or why choose propane?
Yeah. Well, we have to say that there is no optimal propellant combination that works globally for any single application. You've seen also launch vehicles with 2 different propellant combinations in 2 different stages. We're choosing, obviously, going with propane in both stages. It's always a trade-off between performance, your supply chain, your compatibility of the materials, availability. It's several factors. In our case, we found that propane has a high performance, especially when considering its high density. And the high density can be achieved because it has a low freezing temperature, meaning you can actually cool it down to low temperatures that are still compatible with the liquid oxygen temperatures and get this higher density from it. And at the same time, it also has an established supply chain, meaning that availability is not that big of a bottleneck when considering also the high cadence that we want to achieve.
Gotcha. That was a lot. That's why we brought the chief engineer onto the show here. You said compatibility with the temperature of the LOX. I guess that's the thing. Like, you chill down the propane, and as you get it colder, it becomes denser, so you can fit more of it in a given volume of vehicle or volume of structure, right? But also, you don't have a big temperature differential between the propane, the liquid propane, and the liquid oxygen. I could imagine it would be a problem if you had a warm tank and a cold tank and that temperature gradient between.
Yeah.
So that's what you were saying. You can sort of get them close to the same temperature, and they're compatible.
Exactly. They're close to the same temperature at this point.
All right. You also talked about the availability, propane supply, transport. It's all figured out. It's nothing new, so that's a pretty widely available fuel, I guess?
Exactly. It's not an exotic fuel.
Right.
It's used in several industries. As you said, your barbecue burner at home as well.
Well, I don't
Maybe
have
not
space
the same
propane,
grade, but you know, it's something that is already established, not in Europe, but you know, globally.
Globally. All right. How much? I mean, this is another thing to sort of talk about. Are we talking about, it's so hard to get a scale of how much fuel there is in the vehicle.
Yeah. Mentioned earlier, it's roughly 55 tons total weight of
between
the vehicle.
both.
In total, including the structures, and out of that, approximately 35 tons is liquid oxygen and 14.5 is liquid propane. So you can imagine it's a large amount of propellant, and that's still a small to medium size vehicle, but it's still a lot of propellant that we need to fill onto the.
That's the thing that a lot of people don't understand. Like a jet plane, right? A jet plane uses jet fuel, but it just carries the jet fuel. And it gets its oxygen for the combustion from the air that it's flying through, because by definition, air, it's right there in the name, airplane, right? Rockets don't get to do that. In order for a rocket to operate in the vacuum of space, they need to carry their own oxygen to create that combustion when there's no free oxygen to sort of gather from the air. They're not in the air anymore, right?
Exactly. That's why we don't only carry the fuel, but also the oxidizer, liquid oxygen in that case.
Yeah, and there's more than double the amount of oxygen that you have to carry as fuel.
Indeed. It depends on the actual propellant combination and your optimal mixture ratio, but in our case, it's more than double the actual,
All right.
the actual mass.
Well, the rocket seems to be coming alive here.
Yeah, I got distracted for a second seeing
look on the
the
screen.
bleed. That's really, really good to see that we're reaching this point.
Excellent. The clock continues to tick down here, folks. We're now less than 24 minutes away from launch. What are the vents right now?
So it's actually the bleeds of the engine. So we're in the process of conditioning the engine thermally at this point.
Conditioning the engine thermally. All right. And that's a normal sort of thing. That's not a leak. That's a controlled, intentional.
Intentional. This is expected. It means that so far we're still green for launch. Go for launch.
I believe here we've got another bit of video to play for y'all. I'm going to keep watching the rocket here. But if you're just joining us, thank you so much. We continue to count down, now 23 minutes away. Let's roll a video about some production here.
When we set out to start Isar, the world, frankly, looked quite different compared to today. Space is now a critical geopolitical topic.
We have more and more needs to get space access. The number of customers is increasing worldwide.
The market has been shifting quite a lot actually for the last year or so. All very good news for launch service providers as demand is increasing in so many different ways.
You can have 1,000 satellites sitting on a shop floor, but if you don't actually get them into the right orbit at the right time, it's all a bit useless. At this point, the challenge in the space industry is not on a technological level, but a real challenge is how do you build tens and hundreds of rockets? You have to really design for industrial scalability from day one, and that's what we did at Isar.
What is unique about Spectrum is the fact that we have thought about industrialization and scaling very early on. We have a great manufacturing capability. We have a great space launch ecosystem with test rigs and all the capabilities that belong to it.
And so we ended up actually insourcing almost everything, or at this point we own about 90% of the value creation of the entire launch system, which not only allows us to actually scale our production, but it also gives us a lot of independence.
The first step is enabling to assess the space, and then you are getting lots of new opportunities.
Now, if we want to develop a new system or upgrade the current system that we have the capability and the capacity to do so.
When people look into space and into the skies, they don't just see the stars and the planets, but also the potential of, hey, what does space hold for us back here on Earth?
There in that video, we saw some of the automated fiber placement machine, the big robotic arm that was wrapping the barrel. That's so cool. Now, we do need to talk about the mission a little bit here. The name of the mission, Onward and Upward, says it all, doesn't it?
It does. It reflects this relentless drive for progress and improvement. Essentially, Flight 2 builds up on the successes and the lessons learned from the first flight. We mentioned Flight 1. This was a test flight. We wanted to get as much data as possible. Right. Every single trace of sensor was invaluable for us to get to these learnings, transfer them into engineering decisions. With Flight 2, it's slightly different. This is an actual qualification flight. So it's a major step in this process to operational service. With Flight 1, we went from a company that builds and tests vehicles to one that actually flies them.
Right.
And now with Flight 2, we want to transition to the next phase, which is flying them at a high cadence, flying them reliably, and flying them to a high operational service cadence.
Right.
With that, since qualification, we want to validate the major launch vehicle functions and operations in representative flight environments. The same thing as you would do with qualification of another component on ground. And we want to get to as many of the mission milestones as we can. Obviously, with orbital insertion being an intended objective, but as well, along the way, we want to focus on learning, on getting the system verification, getting the confidence that's going to fuel our next missions. So with it, we're going to demonstrate, hopefully, that our system meets the requirements across these harsh conditions. And we know that space is harsh enough for giving. We will hopefully design our vehicle to sustain these very hard conditions. And again, as we said, it's a step-by-step process, milestone-by-milestone process, flight by flight. And we're in this iterative loop right now.
It's like you're sort of forcing yourself to take a step forward. It's not, oh, it's another test flight. Oh, test flight, right? You're not just going to do test flights forever. That qualification flight is a step forwards, which is what you want to do.
Exactly.
Now, payloads. Does a qualification flight mean that there's a payload on board?
Yes, it does, actually. We have 5 CubeSats and 1 experiment on board of Flight 2. These are university projects. And in fact, they've been supported by the European Space Agency's Boost program, meaning that European Space Agency bought this launch slot, or is our customer, and then distributed to these university projects.
Outstanding. So you can see the clock is currently continuing to tick down here just above 17 minutes, T-minus 17 minutes. Let's talk about what success looks like today.
Yeah, so we briefly touched upon that with the qualification aspect of the flight. We're almost exactly 12 months after proving that, you know, we can design and build and launch a vehicle from continental Europe. Now we want to validate these critical systems under the true operational conditions, and also at this point carry payloads into orbit. Right. So we want to go through these individual milestones, starting all the way from ground sequences to liftoff to max Q and so on and so forth. Get as much information as we can, and in the process validate as many systems as we can.
Absolutely. And the important thing here is that you're not just building one rocket. Each rocket is a step forwards to increase your capabilities. You're learning, mature your systems, but this isn't about any one rocket. There are more rockets that you're working on.
Yeah, that's very important to highlight. Again, it's not a research experiment. We don't want to just get one vehicle off the pad and into orbit.
Right.
We want to do that reliably. And for that reason, we have also Spectrum 3 already in the final phases of assembly in our hull, and vehicles 4 to 7 already in production, with major parts, like for example primary structures and tanks, being already manufactured.
Okay. Coming up on T-minus 16 minutes here, folks. In just a second, we should have an update for you. But we'll continue sharing all the different views from around the launch pad. You can see the venting, the chill there happening down at the bottom of the engines. We'll keep rotating the views around for you. Now, some milestones to get here, right? It was only 9 months after the first flight that you came back to the pad for Flight 2.
Yes, so it's a long way. I mean, a lot of points that we needed to cover in this process, going from Flight 1 to Flight 2. It started all with reviews first of what happened, which systems performed well, which didn't, going to engineering changes and making engineering decisions, building these components again, and then accepting the subsystems. So we always start this iterative process, or this process of accepting smaller components and then going into integrated testing, which is what you mentioned. 9 months after the first test flight, we had already stage testing of both Stage 1 and Stage 2 here in Andøya. And with that in parallel, we also had payload integration. Here we can see actually some great footage from our Stage 2 test rig. Really
this was for this flight, right?
This for this flight. This is the acceptance test of our second flight, second stage.
Gotcha. Is that the second stage that's on the same launch mount that the full rocket flies from? Am I saying that correctly?
Yes, that's correct. That is correct. We're using this facility also for stage testing.
All right. So that happened late last year?
Yeah, that was late last year in December. And after that, we obviously also went to Stage 1 testing. At the same time, I think there is a footage of that as well. Maybe we can see that later.
Yep.
But we also went through payload integration, obviously, in parallel, meaning that all these payloads were brought and encapsulated into our fairing. Well, we're seeing now Stage 1 being erected and hot-fired. This is, again, footage from Stage 1 accepting of Flight 2.
The replay from just a couple months ago.
Exactly. And with these 2 milestones, so payload integration, Stage 1, Stage 2 acceptance testing, we verified that our systems can work all together. So, we obviously acceptance test our engines, we acceptance test our electronics, we acceptance test our structures, but then we put everything together. And with that, we proceeded to the next milestone, being a flight readiness review, a final checkpoint or technical checkpoint, showing that the launch system, so ground and launch vehicle, as well as operations, are ready without any open engineering items.
Gotcha. So I got to ask, as the chief engineer, are you involved with the flight readiness? Silly question, probably. Do you run them? Like, who does that?
Yeah, that's a mixture from the technical department, so that will be in my responsibility for the technical readiness, and obviously our mission and launch operations team and the launch director, making sure that the operational readiness is also ensured.
Gotcha. What's the difference? The technical readiness is the vehicle itself, like, is everything installed correctly, the numbers are working correctly, versus the pad operations?
Yeah, but you can think of it that way, making sure that all the technical risks that might be found out or anomalies have been closed, any non-conformances, that's on the technical aspect, and at the same time that operations and procedures are also fulfilled from the operational side. And, a final milestone is then the launch readiness review. So this is very shortly before the launch.
Right.
And it extends also to other systems like weather conditions, launch procedures, making sure that everything's ready for that particular day of launch. And this is also what we passed and ended up being on the pad ready for Flight 2.
In January. We were out on the pad in January, weren't we?
We were 2 months ago. We were actually standing on the pad, ready to go. 1 day prior to the intended launch date, we were standing on the pad and found actually an issue with one of our valves.
Okay.
As we said earlier, we have high standards, that being a qualification flight. So this wasn't something that we could accept and proceed with into flight. And for that reason, we decided to back down, replace this valve, and then be ready again a couple of weeks later to launch again. That in combination with weather conditions, range availability, ended up to us being here now ready for Flight 2.
Gotcha. It always seems like it's valves. Like every time there's a rocket delay, like a valve always seems like a good culprit.
It is also always the culprit, and it's kind of normal. They are, they have to operate at a large range of operating conditions and environments,
right?
Temperatures.
Temperatures.
Exactly.
Yeah.
And it's also complex parts in terms of their tolerances and stacking from a manufacturing point of view. And that's the reason why they're typically the culprit.
I like the umbilical shot here. Like on the left-hand side of the screen, that's the transporter erector, right?
Yeah.
You use that to support the rocket as you roll it out from across the street. We saw that in the video.
Yes,
the AIT is across the street, and you sort of roll across, and that transporter erector supports the rocket, and then it also helps it stand up vertically. Mm-hmm. Here, it's been retracted just a little bit, and all the lines you can see sort of going across. Can you name all the lines? I'm not going to ask you to do that live.
I think I could, but
probably could.
Let's do that now.
But that's the propellants. There's probably some data, telemetry,
exactly.
power.
So it's electrical and power umbilicals. It's fluid umbilicals, both for filling of our propellants and loading and unloading, for our helium loading and unloading. Essentially, supporting all the ground operations. And right upon liftoff, we're going to have a disconnection of all these lines, both electrical and fluid. And after that, there is nothing else holding the rocket. Of course, after the hold and release mechanisms have also opened up, making sure that we can fly to our mission.
Right. Now, stand by, folks, for some more information. We did see that the clock has changed, but we will get an explanation as to what is going on here. Just please stand by as it continues to count down, but it did add a little bit of time there to it.
Yeah. So there are specific checkpoints across the procedures. We have to wait and see if it was an update based on some findings from the current operations.
Yep, absolutely. Today we're not listening in directly to Mission Control. We're letting them focus on their job, which is actually preparing and launching the rocket. Yeah. But as soon as we get more information as to that jump you observed on your screen, we will absolutely share it with you here on the stream.
I have to say it's also kind of weird for me as well. I'm used to getting this feed, getting a live view of the data. Yeah.
Nico wants to leave the stream so he can go get on his laptop and see what the status is. But please stand by. We will get you more information as soon as we have it. So, again, if you're just joining us and you're wondering what's going on, the rocket you see on the pad is Spectrum. It's Isar's rocket that they've built, and this is the second flight of Spectrum here this evening. It's almost said this afternoon, but it's not this afternoon. All the venting and the things you see on the screen here, that's all pretty normal, right, Nico?
Exactly, it's normal. We're at the process where we've already tanked the vehicle.
Right.
Meaning it's fully loaded at this point, both stage 1 and stage 2, both liquid oxygen and liquid propane. And at this point, since it's cryogenic liquids and there is some boil-off, we need to make sure that the vents or the vent valves are open in order to get all this boil-off out of the vehicle, not to pressurize it too much beyond its intended purpose, not to put any stress on it at this point.
Makes sense. Folks, we're going to pause the commentary for just a second and get an update for you. So please stand by. We're going to continue watching the vehicle, and when we come back, see if we can give you a status update on the current state of Spectrum for Flight 2 out here live from Andøya, Norway. All right, folks, here's our plan for now. We're going to continue to listen into our headsets. We'll let you continue to see the views of the rockets. As soon as we get more information, we will share it here with you live. But again, all of these views are live from northern Norway's Andøya spaceport up here. Spectrum on the pad. You can see that it's come to life even there on the side. I love all of the shots. Every shot we change to.
Can go
it's
wrong
a fantastic
with these shots.
shot of the rocket. But we will pause for just a second here and wait until we get some more information. As soon as we have it, we'll be back to let you know what the current status is of Flight 2. All right, folks, as promised, we've got that information. Currently, right now, we do not have clearance for launch from the range. It sounds like there is a boat on the range right now. Something we've seen before, something we've heard about before. That happens at the Cape and things like that. But, of course, we cleared the area, not only immediately around the pad, but downrange. This rocket is going to be going out over the ocean. And so there are areas where they want to keep boats out of, just as an extra safety precaution, right? So here, lacking permission from the range because of that boat violation, a range violation, we are currently in a pause, seeing what the path forward will be. Right, Nico?
Exactly. As you mentioned, flying downrange, we need to make sure that all the safety precautions and regulations are being held. And that's why we have notices for NOTMAR and NOTAR, so both marine and air traffic. And apparently there is a violation, as you just mentioned.
Yeah. It's a good way to keep up with launches because this information is published to the public.
Exactly.
Now, there's fishing boats out there, right? There's folks who are working out there, and you need to make sure that they have the information. We don't just go there on the morning of launch and say, oh, by the way, you can't be out there tonight. This is published days or weeks in advance. There's multiple different places where the information is made available to mariners and the general public. But here, again, to repeat, we are currently standing by. We do not have permission from the range to launch due to a boat violation on the range. We're going to come back with more information in just a second, so continue to enjoy the rocket views and please stand by. folks, another update for you. You've noticed that the clock has continued to tick down. We are waiting for the range to clear. A little bit earlier, we mentioned that the range was currently in violation. There was a boat on the range that was preventing the rocket from launching. Nico, that's got to be frustrating. The rocket's looking ready.
It is. The vehicle seems to be ready, loaded, ready to go. But this is now out of control. Let's hope that it gets resolved as quickly as possible.
And absolutely important for public safety as well.
Yes, it's definitely a precaution that is necessary. But still, it's something right now that we wish wasn't there.
Yep. So, since the clock is continuing to tick, let's continue to talk about the mission here, shall we?
Yeah, we can do that.
All right. So far today, we've been preparing this rocket for launch. And so far this week, there's been a lot of work going. Let's talk about some of the milestones, the fueling, all the things that had to happen to get us here where the rocket was ready to go.
Yep. We can start maybe even before that, like a day before that, which is when the vehicle is being rolled out to the pad and then erected with a transporter erector. All the umbilical connections are being done, all the health checks are being done on particular systems like the fluid system, on valves, on structures, on avionics, on propulsion. And then comes the launch day, which started today. It was an early day, maybe around 11 a.m., 11:30 is when we started rigging the pad, making sure that everything is prepared. And then there are some milestones along the way. Obviously powering on the electronics, making sure that the onboard computers are reading as they should be. They have all the health checks passed. Then again, doing similar checks for fluid system, pressuring the tanks in terms of cycling them initially. And then there is a decision point before going into actual loading of the propellants. So this seemed to work very well. Within our time plan, we were even faster than what we initially thought. I have to say here, operations are running very smoothly. And with that, with the propellant loading, we then have some further checks in order to go into engine conditioning as well. We can still see it actually, at least on our screens, we saw it earlier, the bleed through the engines. This is the actual chill down that's happening.
There you
go.
Yeah.
This is the conditioning. We need to make sure that the temperature in the engine is as we would expect for them to ignite properly and have their nominal behavior. So this is the purpose of this bleed coming off the side.
So you don't want to surprise them with a big temperature change. You don't want them to be a sort of ambient outside temperature and then all of a sudden hit them with cold propellants. You sort of precondition their temperature.
Exactly. Yeah, precondition them and also make sure that the fluids themselves, when they get to the turbopumps, when they get to the thrust chamber, have the nominal or are within the nominal range of temperatures that we accept, to also ensure that the performance of the engine is going to be as we test it on the test rig and as we test it in stage testing.
Makes sense. So I'm going to manifest. Stand by. I just got the call that we are preparing for auto sequence start. We just crossed under T-minus 10 minutes. Let's manifest some positivity here. So I'd love to see
great news.
this launch. But again, if the range does clear as the rocket continues to count down, let's talk about what we would see after engine ignition and liftoff. I'm going to think positive.
Yeah, or maybe also auto sequence, because there might be a term that people don't know. This is the point in time. It's roughly 2 minutes out from the actual liftoff, where the vehicle gets full control authority of itself from the pad. Meaning we enter a point where we do some final checks, some final alignment of our GNC, so guidance, navigation, control. We start going into pressurizing our tanks to their flight pressures. We're going into the final phases of the engine chill down. So again, this conditioning that we mentioned earlier. And then a couple of seconds before the actual liftoff, we have ignition of all 9 engines. And as soon as all the checks are passed, we open the hold and release mechanism. So this is the structural part of the pad that holds down the rocket while it's hot firing. And after that, nothing else holds it back. So we have liftoff.
Gotcha. So it actually starts the engines up before it's released for flight to make sure the engines sort of settle in, I guess you could say.
Exactly. And you can also open it without having thrust. You need this push from the bottom to propel you at this point. And that's where we have a liftoff. In the first phases, right after liftoff, we have a vertical rise. We can see also this animation right now, which is then transferred into a pitch over, or rather getting from vertical to horizontal, because that's what we need at the end to get into orbit.
You'll notice at the bottom of the image there was no boat on the range.
Yes.
Which is why we're able to go into the animation.
Exactly. Max Q is shown here. This is the point of maximum aerodynamic pressure. So this is the point where we have the highest load on our structures. We're still low in the atmosphere, so some density is there, and at a high speed, so we get this high load. And at some point, roughly 2.5 minutes in, we're going to reach main engine cutoff. So we're shutting down the engines in stage 1 and stage separation. This is the point where the second stage detaches from the first stage and then continues to, or first ignites and then continues to burn in vacuum crossing the Kármán line, 100 kilometers.
100
That's the
kilometers.
definition of space, essentially. And after some point, since we've exited the thick part of the atmosphere, we have fairing separation. So the payloads are then exposed because there is no atmosphere anymore to harm them. And while this engine is burning, this is going to be roughly 5 minutes of stage 2 burn time before the so-called SECO, that second engine cutoff. This is when we actually become orbital, but we're not in the final orbit yet. We're in the transfer orbit. We need to wait for roughly half an orbit. It's approximately an hour. You can think of it, we're going once or half around the Earth.
Halfway around the planet.
Halfway around the planet, exactly. And that's when we do the circularization burn. It's a very short pulse of the engine in the order of some seconds. And with that, we are placed in the final orbit, the targeted orbit. And some seconds later, we release the spacecraft into this dedicated orbit. And half an orbit later, so we still coast a bit further with our upper stage, we perform a deorbiting burn. This is where we flip essentially the stage over, do another short burst. And with that, we reduce the velocity and allow it to safely go and enter into the atmosphere.
Back into the atmosphere, right. Being a good space citizen to make sure you don't leave orbital junk up there just floating around.
That's the whole purpose of that, of not leaving any debris in orbit.
Again, if you're just joining us, I know more and more people come and join the stream the closer we get to liftoff. The latest information we had was that we did not have clearance from the range to launch. There was a boat on the range. And this is very important. It's very important that when we launch these rockets, we want to see the flight, we want to get the data, but we also want to make sure that we follow all safety protocols. We keep the public safe, we keep the people that are working out there on the boat safe. So the latest information was that there was a boat on the range that was going to not allow us to fly. However, the clock is continuing to count down right now. So we are going to continue telling y'all about the mission as we've just crossed under T-minus 5.5 minutes. And as soon as we have any more information, I believe the hope is that that boat is able to clear out of the range right here as we get down. We'll be safe, we follow the safety protocols, but there still is a chance that we get the rocket off the pad tonight.
Yes, let's hope so.
Let's hope so. Manifesting the positivity here. Okay. We are now less than 5 minutes away from launch. There's going to be, of course, I imagine there's lots of conversations happening in mission control right now.
Yeah, I can hear some of the operators or imagine them at this point. I'm sure that the pulse is also pretty high for all the operators. It's also a situation that we experienced for the first time. You know, something also outside of our control. You know, we've dealt with unexpected situations in the control room before, technical issues and so on and so forth, but you know, I think this is the first that we have this range issue at this moment.
Yep, and it's all about getting experience. It's experience with the rocket. Even tonight, your team is getting experience on how you deal with launching these vehicles, but also making sure that you follow all proper protocols to maintain public safety.
Exactly.
Absolutely. So we will continue to see if we are able to get that range clear. The call I just heard is that we're go for auto sequence again. Nico's nodding.
I also heard that. That's great to hear, actually.
Okay. Now, Nico, we are at T-minus 4 minutes. You've put so much work into this rocket. I think that you should head on outside and watch the launch.
I would really appreciate that. We're in a great spot, have a direct view of the pad.
Yep.
So I'll be back.
Okay. Get some shoes on, get a jacket, don't close the door on the cables.
Yes.
And let's see if we can
remember that. And yeah, to Spectrum and the team, all you have to do now is send it. Good luck.
All right. Thank you, Nico. And folks, here for the final minutes. T-minus 3 minutes and 30 seconds counting down. Still a chance. If I get any more information, I will share it with you. Nico's going to go outside and see if he can get eyes on the rocket. But here's my plan. I'm going to let you listen in to the sights and sounds of the pad. You can see the venting, you can hear the pumps, all of the different noises. Listen to what Spectrum has to say, because it looks to me like Spectrum is ready to go. If I get any information about the range violation, I will come back and share it with you as soon as I have it. But we are now crossing T-minus 3 minutes away from Flight 2 of Isar Spectrum rocket, live out here in Andøya, Norway. Folks, an update here at 2.5 minutes to launch. I just got word in my headset that we have clearance from the range to launch. The range has been cleared, and we got the go that we are able to give it an attempt here. So, with 2.5 minutes to go, guys, that really does get your heart going. But that's what I wanted to come back on the stream and tell y'all. Let's see what we get. Listen into the sights and sounds of the pad. It's Spectrum rocket. It's Flight 2, the return to flight for Isar Aerospace. Wish them some luck wherever you're watching from. T-minus 60 seconds. The auto sequence has started. "45. T-minus 30. T-minus 10. Let's go, Spectrum. Folks, there at the end, you saw we have crossed the T0, and we did get the call that there was an abort at the last second. This is a normal thing that happens. As we were waiting for the rocket to go, we're going to get a little bit more information for you here, but this is a thing that can happen. Remember what Nico talked about, the different safety checks that happen right at the end, right before launch. It sounds like we didn't quite get there. I'll get you more information as soon as I have it. Please stand by. Folks, we are standing by here as soon as we get more information from Mission Control. It's important to me. I don't want to guess as to what goes on here. I mean, Nico is back with us. Nico, so many different sensors, so many different leads, so much different information. There's a lot of different things that could be happening right now.
Yeah. At this point, we don't have any precise information as to what exactly the reason for the abort was, but we know all the checks that the vehicle does at these final moments. So we need to ensure that all the systems that are critical for mission success are within their required envelope to proceed with flight. So that being tank pressures, that being COPV storage pressures or helium gas pressures.
Right.
Shortly before going into actual engine ignition, we want to make sure that the rest of the system is in a good health to also ensure that we don't have another cycle on the engines themselves. Now, we can only speculate what the exact reason was, but one thing is for sure, it's always a fine balance of making sure you don't have too many checks, but still enough to ensure that you can go on with the vehicle for a successful mission.
Right. As soon as we get more information as to the cause of that abort, we will be back and share it with you. But Nico, you're exactly right. We are not going to sit here and guess about all the different things. Remember, 100,000 different things have to go right in order for the launch to occur. One thing might have been out of bounds, and we'll get you more information on exactly what that was as soon as we can. We might not get it right now, even.
Yeah.
So, again, if you are just joining us and wondering what's going on, in the upper right-hand corner of your screen, you can see that we have a hold. We ran out of time there, and we got an abort right before liftoff. The range did clear. Like right there at the very end, I was able to come back, and I got confirmation that the range had cleared, but the abort kept us from lifting off here. We're going to let you continue to watch the vehicle, and as soon as we get more information, we will be back to share it. All right, folks, we continue to stand by for more information here, but I do want to stress we may not get the complete cause tonight, right, Nico?
Yeah, we need some time to look into it. I'm sure the engineering teams right now already have some understanding of what's happening, but we need to look a bit further to understand exactly what the cause was, and the root cause of that.
So we'll continue to stand by here and see if we do get more information, and as soon as I get more information, we will share it with you. Now, I will say, you should follow along on Isar's social media and their website. Over at isaraerospace.com, you can get official updates from there.
Yes, exactly. And we're always looking for very brilliant people to help us there. So it's great to see, people with interest to contribute to our mission. At the same time, it might not be the outcome we hope for today, but it's still an opportunity to learn a lot from it. And I want to thank also the teams for all the passion and the drive, especially since F1. I'm pretty sure that we're going to be ready to go again very, very soon.
Right. Makes sense. Again, folks, stand by. I'm getting just a little bit more information here. Okay. So the official information here at the beginning of the stream, we did say that we were working with a 15-minute window, and the delays with the range violation and then the abort at the end means that we are out of launch window for this evening, so that will be the end of the attempt for tonight. Again, please make sure you follow along on Isar's social media and the official website, isaraerospace.com. Of course, they'll work to determine what the issue was this evening and see what we have for upcoming launch dates and windows as well. Nico, as always, it's fantastic here being with you talking about rockets.
It was great being here. I'm looking forward to getting here as soon as possible again for our next flight to attempt.
Absolutely. Folks, Nico Parakis, Chief Engineer for Spectrum, thank you so much for joining us.
Thank you, John.
All right. And again, folks, say thanks to Isar this evening, giving us all the fantastic views of the pad. The drone shots were fantastic.
Oh, yeah. They were
both
spectacular.
Inside and outside of the factory. I know that we all wanted to see a launch tonight, but You'd rather be on the ground wishing you were flying than flying wishing you were on the ground. And tonight, we've aborted the Flight 2 for Spectrum's launch attempt. I'm John Galloway with NSF. We appreciate you watching, and we will see you for the next attempt of Isar's Flight 2.